Hi everyone, let's talk about waves and sound. So starting off, waves is just a disturbance in a medium. And what I'm talking about a medium is simply what the wave is traveling through. For water, it's easy, it's water waves. So water is the medium. The sound of my voice is traveling through the air. Earthquakes, the medium will be the earth. So a medium is simply what the wave is traveling through. And it also controls the speed of the wave. If we change the medium, we change the speed of the wave. So think about like a string instrument like a guitar. The string is the medium. So if we tighten the string, we've changed the medium, we've changed the wave, we changed the sound. We loosen it up, we've also changed it. It's the same type of wave, but now the wave's not traveling at the same speed because we changed the medium. But the main thing about waves is waves carry energy from one place to another. They don't carry matter. So a water wave doesn't carry that single set of water molecules from one side of the ocean to the other. It carries the pulse. Like if you see somebody or a group of people do the wave at a ball game, okay? Those people really don't move. There's not a group with their hands up running around the stadium. It's simply a bunch of people standing up and sitting down, then the next group standing up and sitting down, then the next group standing up and sitting down. And that pulse is what you see travel through the medium, which is the people. That's the wave. So waves come in two different types of classes, mechanical and electromagnetic. Mechanical waves are what we mostly think about, waves that we can kind of see or that we can affect, like water waves. If you shake a rope up and down, you're creating a wave in a rope, that's a mechanical wave. You see a slinky go back and forth, that's a mechanical wave. So they're physical waves. Electromagnetic waves are any of the electromagnetic spectrum, ranging from radio waves all the way up to gamma rays. And all electromagnetic waves travel the same speed in space, 3 times 10 to the 8th meters per second. And doesn't matter which type they all travel that same speed. And so we give it a special letter, we call it lowercase c. So in the world's most famous equation, E equals mc squared, that little c is 3 times 10 to the 8th. And all electromagnetic waves are transverse. Mechanical waves can be either transverse or longitudinal, but electromagnetic waves are always transverse. Now I mentioned two things there, longitudinal waves and transverse waves. So let's talk about those. So those are the two different types of waves, is longitudinal and transverse. To get into details, a longitudinal wave is one where it vibrates back and forth as it's also moving back and forth. So I think about stretching out a slinky like in this picture, and then just flicking the slinky back and forth so it sends a pulse through the slinky. So at some points the little loops are closer together, and at other parts they're spread apart. Where they're close together, we call that a compression. That's the high pressure zone. That's where things are built up. Where it's spread apart, we call that rarefaction. That's the low pressure zone where things are also more spread apart. Compression pushed together, rarefaction spread apart. And one of the best examples of a longitudinal wave is sound. Think about a speaker moving back and forth. The speaker moves out and back, out and back. So that sends out a pulse, pulls it back. Compression, rarefaction, in a pattern that matches up to the sound that we hear. But most waves that we think about are transverse waves. A transverse wave is one where you move something up and down as it moves sideways. So if I shake a rope up and down, the motion of the wave is up and down, but the wave travels sideways. And so it's traveling across or transverse of what's going on. So that's a transverse wave. And for a transverse wave, that's the one that most waves that we think about are. Whether it's light or water waves or anything like that, most waves that we think about when you hear the word wave are transverse, except for sound. And they have a couple of different points where a longitudinal wave has compressions, rarefactions. A transverse wave has a crest and a trough. And we mostly use transverse waves because they're easier to label and to diagram. So for this one, it's got from one crest to the next crest, that's one wavelength. Or you can go from one trough to the next trough, that's one wavelength. Amplitude is from the mid part of the wave up to a crest, or from the mid part of the wave to a trough. And we'll get into those properties here in a little bit, like right now. So there are several properties that all waves have. All waves have a period, which we designate as a capital T. It's measured in seconds, and it's simply the time it takes to complete one wave. And so the time it takes for one crest to go by till the next crest comes in. That's one period. Frequency is the inverse of a period. Frequency is how many waves pass a point every second. And so, like on your radio, it may be so many, like 101 megahertz. That means there's 101 million waves passing by your antenna every second. So frequency tells you how many, period tells you how long it takes. So if I say a wave passes every 10 seconds, that's a period. If I say 10 waves pass in a second, that's a frequency because it tells you how many. So always look at the question, does it tell you how long it takes? Then that's a period. If it tells you how many go by in a certain amount of time, that's a frequency. And that time really should be in seconds. But you can go from one to the other because they're the inverses of each other. So period is 1 over the frequency. Frequency is 1 over the period. So if you've got one, hit inverse, you've got the other one. Another property is wavelength, and that's simply how long one wave is. And that's kind of obscure, but mostly it's from one part of a wave until that same identical thing shows back up again. So from compression to another compression, that's one wavelength, or from one crest to another crest, that's one wavelength. Or in this picture here, that where the wave starts to go up to the next time that wave starts to go up, that is also one wavelength. So here going up to here going up, so it's between two identical parts. Amplitude is the height of a wave. Now it's really hard to judge that with a longitudinal wave, so that's why we mostly use transverse waves. But for this one, amplitude is from this midpoint up to a crest, or from that same midpoint down to a trough. That should be the same distance. So up and down, in this case, is your amplitude. The distance side to side is your wavelength, looking at the picture here. Now, amplitude could represent a bunch of different things. It's how much energy the wave has. So it could be how bright it is, or if we convert a longitudinal wave into a transverse wave, the amplitude would be how loud it is. So it's how intense the wave is. Another property of a wave is its speed. We've already talked about that the medium controls the speed of the wave. But the way you find the medium, or the speed, I should say, is using the wave equation, where velocity equals wavelength times frequency. That little upside down y is the Greek letter lambda. And it is, or it stands for wavelength. And this stands for frequency. So lowercase f stands for frequency. But it's that medium that controls how fast the wave's moving. Another thing that this equation tells you is that since the medium controls the speed of a wave, if you increase the frequency, so if we keep the velocity the same, but increase the frequency, the wavelength has to actually go down. So think about an instrument like a xylophone or the old-fashioned pipe organs. It's the small ones that play the high notes and the large ones that play the low notes. Just like with most instruments, the big ones play low notes and the small ones play higher notes. The higher notes have a higher frequency or high pitch, and so they need to be smaller to match the wave. The big ones have a lower frequency, so they need a longer wavelength, a bigger size to get the same velocity, because again, the medium controls the velocity of the wave. Now, the one exception to that is electromagnetic waves. For them, we're not worried about electromagnetic waves going through water or something like that at this time. So we're just going to use air and space. In air and space, all electromagnetic waves essentially travel at 3 times 10 to the 8th meters per second. All right, now here's a couple of examples about converting between period and frequency. So in this one, we have a frequency of 20 hertz, and we want to know the period. Well, period and frequency are inverses of each other. So I'll just take that hertz, that tells me it's frequency, put it in there, so it's 1 over 20. 1 divided by 20 is 0.05 seconds, so it takes 0.05 seconds for one wave to pass. Over here, we've got a little bit of the exact opposite. We've got a wave passes every 5 seconds. So that tells you how long it takes. So that's the period. I want to find the frequency. So if I put 5 in for the period, I want to find frequency. I do my little supersymmetric and swap these two, just cross multiplication. And I get frequency is 1 over 5, which when I divide it out, frequency is 0.2 hertz. So again, if you know one, take the inverse, you've got the other one. So another way that we can use our equations is to find the speed of the wave. So in this case, I've got an example where the wavelength's 2.5 meters, frequency is 136 hertz, and I want to know the speed of the wave. Now this wave equation works for any wave, no matter what type it is. So it's just velocity equals wavelength times frequency. So my wavelength's 2.5, frequency 136, just multiply them together, and I get a velocity of 340 meters per second. On this other one, I go a step further. I give you that a wave passes by every 4 seconds. So that tells you how long it takes the wave to go by. So that's the period that I need frequency for my equation. So I'm going to find the frequency. Period equals 1 over f. Plug that in. Supersymmetric, simple cross multiplication. And I get a frequency is 0.25 hertz. Now I go back and see that the distance between crests is 6 meters. Well, from one crest to the other crest, that's a wavelength. So my wavelength is 6 meters. So I take the wavelength of 6 meters. The frequency is 0.25. Again, multiply them together. I get a velocity of 1.5 meters per second. Another example. Again, this time I want to find something else besides speed. So I'm given the speed of this wave is 24 meters per second. Frequency is 3 hertz. Start off with the wave equation. Velocity is 24. Frequency is 3. Divide to figure out the wavelength, and I get a wavelength of 8 meters. If I go a little bit deeper in this, now that I've been given the period is 5 seconds and the speed, I want to know the wavelength. So in this case, I actually need to find the frequency first. Again, just like we did last time, cross multiply. Frequency is 0.2 hertz. I know the velocity is 60. Wavelength is what I'm looking for. Period is 0.2 frequency is 0.2 seconds. Divide, I get a velocity of 300 meters per second. Now we mentioned that sound is one of the best examples of a longitudinal wave. If I didn't, I should have. But sound, it travels through air, and air can change. Air can get warmer, it can get colder, it can become more dense, it can become less dense. And so since that medium is changing, then the speed of sound would be changing. So we have an equation that kind of takes care of that, at least as far as temperature is concerned for us here. Now, so the speed of sound is equal to 330 meters per second plus an additional 0.6 meters per second for every degree Celsius. Now this first number, 330, that may change depending on location. I've seen some use 332, some use 331, but I'm going to go ahead and for this example use 330 for our situation here. but the temperature's got to be in Celsius, and I'll give that to you, or you can either easily figure it out. And so if we use this, this will still be a velocity, so we can still use the wave equation. But if I just want to figure out the speed of sound at a certain temperature, let's say 30 degrees Celsius. I've got my 330 plus 0.6 times degrees Celsius, so 0.6 times 30, well, that's 18. So just 330 plus 18, a velocity of 348 meters per second would be the speed of the sound at that temperature. Now, if I take that, and let's say I want to find the frequency of the wave. Again, the same temperature, so we're going to end up having the same velocity, but now I'm given a wavelength of 0.25 meters. I can use the wave equation, velocity is 384, wavelength 0.25 meters, I want to find frequency, divide, and I get a frequency of 100 or 1,392 hertz. So same setup, just now we may have an extra step to figure out the speed of sound at that temperature. Now, if it's not sound, a wave in water or anything like that, we don't have to use this equation. This is only for sound in air, not sound in water, not sound in a solid, just in air. One thing that can happen is two waves can actually collide into each other and create interference. But they don't really collide, they actually pass through each other. And they can do it in several different ways. And two of the ways is with what we call constructive and destructive interference. So constructive interference is when two waves overlap and their amplitudes actually add to each other. So the wave grows larger just for that instant the two waves are overlapping. And in this example here, I've got this one wave pulse. Let's say its height is 0.5 meters, heading this way. Another wave pulse heading towards it, it's also 1.5 meters tall. At the moment the two overlap, we'll get an even larger crest that is 1 meter tall. So 0.5 plus 0.5, 1 meter tall. And then the waves simply pass through each other because they're a disturbance in the medium. They don't actually collide with each other. This wave will actually go through and pass through. This one will overlap that one and pass through and just keep going on their way. They're only going to interfere at that moment where the two waves overlap. And this bigger amplitude means that if it was a sound wave, if that pulse represented a sound wave, it would be louder there. If it was light, it would be brighter. And so it would be more of whatever it is. The flip side of this is destructive interference. This is where the two waves overlap and actually reduce each other. So let's say we have another pulse here that's 0.5 meter tall, another pulse here that's on the bottom, so now it's a trough, that's also a 0.5 meter in depth, let's say. When they overlap, well, this one's 0.5 meters up, this one's 0.5 meters down, so this hill completely fills in this valley and we get nothing for just that instant. And then this wave will actually pass through that point, still continue on. This wave will pass through that point, continue on as normal, unaffected by what happened. But for that brief instant, they completely canceled each other out. And so one of the best examples of this is noise-canceling headphones. Noise-canceling headphones actually sample the sound around you and play that sound back out of phase, where instead of for a sound wave, instead of a compression, it plays a rarefaction, and thereby canceling out that background noise, or at least trying to, so that everything's quieter around you. Now what happens is a lot of times these aren't in nice, simple packets. They come in patterns, like one wave after another. So as they pass through each other, they're going to alternately be constructive interference and destructive interference. So they'll get louder, quieter, louder, quieter, louder, quieter if it's a sound wave. And we call that beats. When waves pass through and they alternate, get stronger, weaker, stronger, weaker, due to that alternating constructive and destructive interference. So this is supposed to represent that, where it's quieter, it's louder. So here, two, let's say, crests overlap. Here, a crest and a trough overlap. Maybe here, two troughs overlap. This is just kind of giving the overall pattern of being quiet, louder, if this was sound. If it was light, it'd be dark, bright, dark, bright. But how we figure out the beats is it's simply the difference in the two frequencies. So if I play two sound waves, one has a frequency of 75 hertz, the other one has a frequency of 70 hertz. I play them both at the same time, you're going to hear a pattern of loud, quiet, loud, quiet, loud, quiet that matches up about 5 of those every second. So you'll have 5 loud, quiet, loud, quiet, loud, quiet, loud, quiet, loud, quiet every second. And so you can listen for or measure those beats and tell the difference in the frequency of those two waves. And that could be how you can tune an instrument. Play two notes together, you hear that wobble, and then you adjust one until that wobble goes away, and then those two instruments are now matching frequencies. Now, another thing that happens if you have the same wave get reflected back onto itself, you can get what's called standing waves. Now, you've seen these before, and you've probably done them, is if you tie a rope to something and then shake the rope, you'll see it kind of, if you get the right frequency, it'll actually kind of vibrate in sections. And that's called a standing wave. So we've got this wave going down. When it hits, reflects off, and the reflection will be the exact opposite. And you get a pattern like this, where the wave's going down and reflecting back onto itself. So it has these sections. By the way, this top part, where it's the widest, we call that an antinode. That's where the amplitude's biggest. The part here where there's almost no distance between, we call those nodes. That's where there's no disturbance. You can actually touch a node and not mess up the wave. But if you've got a wave in a string, you touch an antinode, you actually kill the wave. But the part where it's the greatest here, biggest separation, that's an antinode, where the little separation here, here, and here, those are called nodes. Now, that's one wave. What if we shake our hand faster and create more of these? So here we've got a wave going down, it's reflecting back onto itself, and you can tell the number of waves that you have by counting the sections. Every 2 sections is one wave. So I've got 3 sections, I've got 1.5 waves. If I look down at this one, I've got 6 sections. So that means I've got 3 waves. So if the distance from this end to this end was 6 meters, and I got 3 waves in that length, I can figure out the wavelength of my wave. I simply take the total distance divided by how many waves I have. At 6 meters, 3 waves. So that means the wavelength of this wave that's going through and bouncing back onto itself is 2 meters. That's the end of the first lecture about waves. I'll have some more coming to you in a later episode. Thank you very much.